Hey everyone, welcome back. Today we're going to be taking a look at domain warping in TouchDesigner. This is very near and dear to my heart. I love the domain warping technique, and it's something that I've been interested in for quite a while. It was actually one of the things that first got me into kind of generative art many years ago, and it was one of the first algorithms that I became just kind of like infatuated with from the very beginning. Um, So this is a look at the domain warping system we're going to build today. These systems are almost infinitely extensible, so this is going to be kind of like the basic setup. And then there's going to be a ton of ways that you can extend this on your own to achieve truly an infinite number of different effects. So just to kind of get a sense of where we're going, can show some of the parameters we have here. We can change our noise just by using some sliders that we'll be definitely building. We can increase or decrease our amount of warping, warp it more in one direction than the other. And this is all with a very, very simple setup. So you can see once you kind of start to layer things in, how the complexity can really start to emerge. So before we jump in to some of the code, I wanted to first just kind of come back and mention a couple of the resources that I used when I was developing this the first time and second time and third time, as those might be helpful to others. So one is this blog post, Domain Warping Interactive Introduction. It's very good. It has some pseudocode, and this article was, I think, one of the best explainers as far as the concepts behind domain warping. We have Inigo Quiles, who is the master and legend in domain warping. I'm sure everybody who's interested in this has seen his work before. So definitely tons to explore and uncover there. Darian Brito is a TouchDesigner artist and generative artist who has used domain warping in the past to create this edition of works. It's very cool. He's pretty phenomenal. And this isn't as much about like the technical code, or at least there's no actual code in the blog post, but he goes into some of his methodology, which is pretty interesting and just nice to see a really cool, beautiful implementation of these algorithms. And then finally, Palm Drop, which is actually how I discovered domain warping first. And this is a little bit of a different technique that I've also implemented, but I think it's a little bit less straightforward. So I'm going to stay away from this for today's tutorial, but for those that are enterprising, there's definitely a ton to be gained from just kind of digging through these resources and also the rest of the websites. All three of these, Palm Drop, Darien, and Inigo, are phenomenally deep websites that have just so many articles. So, anyway, this is kind of what has inspired me and what has given me a lot of the information that I put together to create the algorithm that we're going to take a look at in this tutorial. I'm going to quickly just update my resolution here to be square, and then we can jump inside and get going with this. So before we jump into actually writing the program of the shader, I want to just kind of go through a little bit of discussion about domain warping, kind of what it is, and add some intuition to what's really going on under the algorithm. So I'm going to first just kind of remove all of our warping. And we can see that we have kind of here on the left, we have some points. And then here on the right, we have our actual domain warping algorithm output. And I'm actually going to just remove the rotation, and we'll put that back in once we're building our program. But now there's a pretty one-to-one output. So if I change my period we can see things kind of zoom in and zoom out. So these points are reflecting the XY domain that our noise algorithm is then using to generate its final texture. So any warping that we do is going to be reflected in these dots as well as in our texture. So we can see that when I increase just the warping on the X direction, and maybe it'll be easier actually if I have these parameters up here. So if I increase just the warping on the X direction, you can start to see what happens, and that is that our domain literally gets stretched along the X, and that stretching is because each of these points is simply moving to a different location on the X-axis. So what our warp is really doing is saying, okay, for every point on the X-axis, move it by some amount according to some function, and now that's the new point. Similarly for Y, and by compounding these two warp factors together, we can start to aggregate some pretty interesting dynamics. Now, you'll notice I have this number of layers. I'm actually going to turn that down to just one, so we have only one layer, and we'll come back to what the multiple layers is in a second. But for now, it's just important to understand that this warp factor is really what's determining how far our newly sampled or newly calculated point is going to be from the original point. And then I mentioned that the new value is determined from some function that we use. And what that function is has a big determinant in the ultimate kind of visual aesthetic of our domain warp. In our case, we're using a noise function, specifically a fractional Brownian motion noise function, which is a noise function that adds several different octaves of noise together to create a little bit more of an interesting pattern. So the other piece of kind of machinery that we have to change our visual aesthetic is by actually changing that noise. So if I increase my warp factors a lot, and we can see that we're really warping over on our noise. There's a ton of motion, and our points are becoming pretty crazy. So to recover our initial formation, which is kind of our square grid, instead of changing the warp factor, I'm actually going to turn down the amplitude and gain of the noise function that we're using to determine the warp. And so this shows you the two different components that are going into the final result. So by increasing the amplitude and the gain of our warping function, which is the noise, we can start to get either finer grained detail in our warp by increasing the gain, or just increasing kind of the distance and amount of our warp by changing the amplitude. So putting these two things together and being able to tweak that warp factor as well as the components of the noise that are actually being used in the warping calculation give us a lot of control over the algorithm and allow us to create some really interesting, complex works from a relatively simple piece of code. So hopefully that builds a little bit of intuition as far as what is going on when we're talking about domain warping and what some of the cool effects can kind of be a result of. So without further ado, I think it's probably time to jump into our actual domain warping algorithm. So I'm going to keep the visualization and not rebuild that. That'll just be included in the project file for Patreons. But I am going to rebuild this main warping algorithm. So this is just the color lovers picker palette. I'm not going to delete that because I think it is pretty familiar. And everybody could just go grab that from Olib or the internet or wherever else. I will at this point, though, delete the rest of our domain warping. And we can start to rebuild that from scratch. So we'll start off with just a classic GLSL multi. And the only thing that we're going to need to wire into this GLSL multi is going to be our palette. Now, I already have this component set up for the tutorial that's going to have all of these components, parameters. So I'm not going to recreate this component just to save a little bit of time in the tutorial. I don't think anybody needs me to show you how to create parameters. So I'm going to leave those parameters, and I'm just going to rebuild the shader kind of using these parameters as just kind of given, understanding that everybody can either create a component and easily add these parameters themselves, or just grab the actual component from my Patreon. So first things first, we just need to set up our shader a little bit, and so for that, we'll use a custom resolution. We'll use the resolution from our parent component. We'll also make sure it's a 32-bit float on the pixel format. And then we'll go in and we'll change our extend UV mode to the extend input UV mode parameter that I already have. This should be set to mirror or repeat, and that will let us sample even if we have a UV value that's greater than 1, which is the case a lot of the time once we're doing this warping, because your domain starts in 0, 1, but can change very quickly once you start to concatenate different warps together. Okay, so the rest of our work is going to be pretty much in the shaders. So I'm going to grab my VS Code, get that over here. And great, now we can get going. And just give ourselves a little bit more TouchDesigner room. Very good. So, first thing that we need to do here is actually just set up a noise function to actually get ourselves some noise values. Now, there's a ton of noise functions that you can find online, but I think the easiest one is to just use TouchDesigner's built-in simplex noise. So I'm going to create a float function, and I'm just going to call it noise. And actually, I'll call it noise function. And then this noise function is going to take in a vec3 that we'll call position. And then we are just going to return td simplex noise that will take in our position. And that's that. This td simplex noise is a built-in TouchDesigner function, so you don't really need to do anything different than that. And then we can say something like a vec3 uv equals vec3, and then we'll take our vuv.st, and then just a 0 for our z component. So now if we output our color using this uv, whoops, it's a 3-component vector, we can see that as we expect, we have this UV nicely mapped out here. Now we can say float n equals noise function, and now we can just pass our new vec3 UV in here. And now instead of passing UV through our color output, we can just pass the output of this function itself. And if we make the alpha 1, now we can see that our simplex noise is indeed working. And this looks similar to the simplex noise functions that I'm sure you're familiar with from other places. So the next thing that we want to do is work out a little bit of period and other adjustments that we can make because we want the kind of algorithm here to be able to be zoomable, right? We don't want it to just be kind of zoomed in this far. And so to do that, we need to add a couple of uniforms. Sorry about the typo. So now we open up our parameters over here on the GLSL. We can start to do a couple things. I know I'm going to need an aspect ratio, so I'm going to give myself that aspect ratio. I'm going to further give myself a period uniform. I'm going to give myself, well, I'll use a period uniform for now, and we'll add the rest later. So I'm going to just drag and drop that period from my parameters, and then my aspect ratio is going to be the y component of my resolution divided by the x component of my resolution. Now here in my pixel shader, I just have to define my u aspect and my u period. Now what we need to do is actually apply our transformations. So we'll apply our domain transformations, and we should probably call this something like apply pre-warp domain transformations. And so first, we want it to be centered on 0, 0. So this will be UV minus equals 0.5. Now we are centered on 0, 0. And then we can do UV times equals U period. And so now as we move our period, we see that our domain is indeed kind of zooming. Now, sometimes the period, like if we look at a regular noise, top, as we move the period up, we zoom in, and as we move the period down, we zoom out. That's the opposite of what's happening here. And so we can fix that pretty easily by just doing a 1 over. And now our period is going to be kind of that same move the period higher to zoom in, move the period lower to zoom out. Set the period back to 1, or maybe something a little bit lower for now, like 0.5. And so now we have kind of something working that will be able to pull in our domain, apply a noise function to it, and then return a value of our noise. So this is great, but this is just returning our actual noise itself. We need to be doing something a little bit different. So I'm going to use this FBM function that I've used for a while. I'm just going to copy and paste this in here, and we can use this, our noise func here instead of our simplex noise. And then we're just looking for this u gain variable, or uniform rather, which we can add as well as a u lacunarity. Now, what's my other error? Oh yes, our amplitude. And so these are the other kind of noise value parameters, which we can just add to our shader. So I'm not going to go further into this, but essentially each time what this little loop is doing is just sampling different noise functions each time it goes through the loop and accumulating those values with decreasing intensity, meaning each additional layer is adding detail, but the detail is smaller. And so that's what can lead to some cool kind of more organic looking patterns because there's more details. Highly recommend Inigo Quiez's FBM article. It's truly the Bible on this thing. So here's the function. And then to finish adding these uniforms, we just need to add uGain, uLacunarity, and then uAmplitude. And now, if I change this noise funk here to FBM, we can see our noise function, and changing these parameters does show us some different styles of the noise, and so that's working pretty much as expected. Now we're still not doing any domain warping, but we do at least have a more interesting function to use to generate some noise. So now the key missing piece is to actually build that warping function. And so for that, we'll take a void function, I'll call it warp, and then we'll use an in-out vec3 that I'm going to call uv. This means is that we're just going to edit the actual UV coordinates in this function. So it's not going to return anything. It's just going to act on whatever we pass into it. Now, if we go back to our visualizer, and there we go. We go back to our visualizer. See why these points aren't working. Ah, yes, I deleted my translate. Okay. I'll come back to that in a second, but basically I just needed this little speed chop, which is translating my noise. And then the translate speed. Okay, actually, take that back. So what I need to fix this is a translate. We want to translate in here as well in our new noise. So I will just call this uTranslate. And then the Z component of the translate speed, or of the translate, I want to use rather a speed chop. And I'm going to use a parameter to grab my translate speed parameter and then use that parameter to actually run the speed chop. And so then I can drag and drop this translate speed onto my uTranslate Z component and make the components 0 for the other two. Now in my pre-warp, I can say uv.z plus equals, or actually it's just uv plus equals uTranslate. And then I just need to add a uniform vec3 uTranslate up here. And now we can see my noise is translating. And now to tie it up to our previs, I just need to update these references since I deleted the original component. Okay, so now we can see that changing these different values does indeed change kind of correspondingly our two pre-visualization and actual visualization here. So what I'm going to do is now build out this warping function. So we'll start the warping function with just declaring two variables. That'll be dx and dy. And actually we can make them equal to 0. So dx equals 0, float dy equals 0. And this is going to be a value that we then accumulate. So we can say, and then add to our UV. So you can say dx equals, and here's where we actually use the noise function to help us out in our warping. So that noise function, in our case, is this FBM. And so we can say our dx is equal to FBM noise, in this case, just taking the UV that we pass in. And we'll do the same for dy. And then uv dot x plus equals dx, uv dot y plus equals dy. This is kind of the most basic warping. And so now I'm going to actually get rid of this, and because we don't actually want to visualize our noise alone anymore, we want to visualize the warp. And so we're going to go back to visualizing our UV for just a second. That's not super helpful because of our period. And so, yeah, we can see it looks nice when our period is low, but we lose a lot of information when our period's higher because we just can't visualize it. So what I'm going to do instead is actually take advantage of that input and find a palette. And so our palette will be texture. We'll grab just the first input because it's the only one that we have. And we can take just vuv.st right now. And then our color can just equal our palette. So that is very straightforward. It's literally just taking this palette right now and translating it directly. But what happens if instead of taking vuv.st, we take uv.st for our sample? Now all of a sudden, as we change our period, our sampling is changing because we're actually using the transformed UV coordinate to do that lookup. So if we apply our warp to our UV, we can now start to see our palette as a visualizer, or rather use our palette as a visualizer for our warped domain by simply looking up colors from that palette using our warped domain as the lookup value, which some people will, I'm sure, be astute and notice is very similar to something like a displace functionality from a displace top. So you may ask, why use this instead of a displace top when a displace top is easier and I don't have to code any of this GLSL? The reason for that is what we're about to get to next, and it's really the power of this technique. So this is cool, right? If I increase my amplitude and gain and just kind of like play around with the period and stuff, I can start to get some cool shapes. But this doesn't really look any different than if you just take a noise and then like wire it into another noise, right? Like, especially if my period is a little bit higher and I make these resolutions better. what is this? Probably this. Okay. And yeah, so like this looks pretty similar to what we got going on here. And that's just not that interesting. How do we make it more interesting? Well, we can warp, but warp recursively. And so what I mean by that is going back to something that's a little bit easier to visualize. So right now, we're warping with just one layer. And keep your eye over here. Nothing should change over here yet, but it should over here. As I increase our warp layers, we are kind of iteratively warping, and so that results in a more warped texture the more number of times that we apply that warp. And the reason for that is that you take the warped coordinate and then apply a new warping to that warped coordinate itself. That aggregation is somewhat similar to what we're doing here in the FBM noise, and it allows for, again, the aggregation of smaller scale details and more interesting patterns. So the way that we can implement that is pretty easy. We just use a little for loop here. So you can just say for int I equals 0, I less than, let's say, 5, I plus plus. And so here, we're actually going to move our dx dy up into the for loop. And we can just use plus equal. And just by using plus equal, now we are every time aggregating this noise lookup and adding it to our dx. Now, if we also add it to our UV every loop, we can see the effects start to compound. And now if I decrease, well, I guess we don't have a uniform warp number, so we can add that. U warp layers. Uniform int u warp layers. And now we can just use that u warp layers instead of this 5. And now we can see that as we increase, we go from 0 warp layers to 1, or rather 1 to 2. We can see some of the detail starting to form. And then as we add more and more warp layers, because we're accumulating this, we can start to see the effects really push and pull and come developing these really cool swirly lines. The reason for that is obviously because we're using this UV coordinate to calculate our FBM. And we're changing the UV coordinate every loop by accumulating the dx dy to it. One other piece of control that we probably want to have is a warp factor. And so this is what I have this uniform warp factor parameter for. Uniform vec2 u warp factor. And then we take this u warp factor, and here we can apply it right here. So we can say u warp factor x times FBM noise UV. And then the same thing, but with the y component for dy, and that's a times. And so again, over here now, if I change my warp factor, now we have a little bit more control over how much warping is actually being applied in both of those directions. Something else that we might want to do is not have the scale of each warp be the same. Maybe you do, maybe you don't. But decreasing the scale for each warp can lead to different effects. So we could say float scale equals 1. And then in every loop, we can just say scale gets divided in half. And then we can add scale times dx to our UV. And so now each layer is adding a little bit to our warp, but it's not adding the same amount. And so then changing this value can lead to somewhat substantial differences in the effects. That's obviously pretty crazy. And if you go like super high, then obviously our effect of each layer is going to be a little bit less. So I think 2 is a nice happy medium, but there are a bunch of different things to explore there. So I'll leave that to you. But this, I think, does give just a little bit of a different look and a little bit more variety kind of across scale. Oh, one other thing that we want to do is probably use a different noise value for our X and Y directions. So to do that, we can just add some arbitrary vector to our UV when we're calculating the Y component. And that way it's just not the same. And you could even add an extra translate and translate this component as well, just to get even a little bit of extra motion in your effect. The last piece that you may want to do is add some rotation in between each warp layer. For that, there's a really nice rotation macro. You can use this I got from Fabrice Niet on ShaderToy. And so you just pick some radians and you can multiply a vec2 by this rotate to implement rotation. So to do that, we can just say uv.xy times equals rotate, and in this case it can be anything. As long as I put a semicolon afterwards, it can be anything. And so now we can see just different rotating values give us different results. And the way to think about this is we're rotating the domain by this number of radians in between each warp layer. So you could also do something like define pi 3.1415141597, I think, something like that. And then define this in terms of pi, so maybe it's like pi over 6, and we rotate it 30 degrees each time. Now, this is getting pretty close to the bare bones basics for some domain warping. And so I think it's probably a good place to stop this first tutorial. I will just come back and focus once again on our full domain warping output here. Oops. We can just see that, again, we have a lot of the same behaviors. We have the ability to change our warp factor, kind of increase and decrease the period, increase the gain or amplitude of our distortion, and really generate some pretty compelling patterns with very minimal work. The true beauty of, I think, this domain warping algorithm is how extensible it is, and so I strongly recommend everyone to dive into this, look at the resources, come up with some creative solutions or some creative ideas on how you can kind of take this algorithm and push it further in your own directions. I'm excited to see what everybody comes up with, so certainly let me know. And as always, thank you all so much for the support. It means a lot to me, and I am very happy to be able to help everyone on their creative endeavors. So with that, thank you all, and I will see you next time.